In this video, I want to talk about how we can consider linear transformations and corresponding matrices as vectors themselves. And given that introduction, you may wonder, why do I have matrix addition and scalar multiplication up on the screen? Well, that's where I want to start. I want to start by just really quickly defining matrix addition and scalar multiplication. So if we have two matrices of the same dimensions, so both of these matrices here have 3 rows and 2 columns, then I can add them, and I add them term by term. So I add 2 and 0 to get the top left term of this matrix. The resulting sum of the matrices is 2, and then I add -2 and -3 to get -5. And I go through all these entries. 0 plus 2 is 2, 3 plus 2 is 5, 5 plus 4 is 9, and -6 plus 8 is 2. And I've added these two matrices. So again, I'm doing this entry-wise. The way that I got this 5 here on the right was adding 3 and 2. I can similarly multiply any matrix by a scalar entry-wise. And what I'll do here is, to get the top left entry, I'll multiply my scalar -3 by 6 to get -18. And then -3 times -1 is +3, and so forth. So each entry in my resulting matrix is obtained by multiplying the entry in the first matrix, in this case 1, by the scalar -3, and that goes in the corresponding entry of my new matrix. So that's matrix addition and scalar multiplication. It's really simple, and there is no way I would have taken the time to make a video just about how to do matrix addition and scalar multiplication. So hopefully you didn't close the video already and say, all right, I know how to do this. What I want to talk about is why. Because sure, you see these two examples and you say, okay, I believe that if I have two matrices of the same dimensions, I can add them in the way you presented. And I believe that if I have a matrix, I can multiply it by a scalar. But why? Why are we doing this? What is it actually telling us? And this is where we go to linear transformations, because all of these matrix operations, we'll see matrix multiplication as well, where we multiply two matrices. They're all about thinking of matrices in terms of linear transformations. So this is going to look a bit abstract, but I'll immediately go back to our example. If we have linear transformations, we can also add them, and we can also multiply by scalars. So if I have a linear transformation between two vector spaces and another linear transformation between the same two vector spaces, and if this is a bit too abstract, we can think of, like, for instance, maybe V is R2 and W is R3, if that makes it a little simpler. We can add two linear transformations. And the way we add two linear transformations is we need a rule for what we do with a vector. We take any vector in V, and the output vector in W we obtain by first plugging V into T, right? Taking T and mapping V into W, doing the same with S, and then adding the resulting vectors together. And similarly, we can multiply any linear transformation times a scalar, and we get a new linear transformation between the same two spaces. And the way this works is that a vector V, well, we map it into the new space using T, and then we multiply by a constant. Okay, as I said, super abstract in general. Let's go back to our examples here. So these are the two matrices that I used before. These are both 3 by 2 matrices, and that means that they represent linear transformations from R2 to R3. Remember, the number of columns of a matrix tells us the dimensions of the input space, or the domain, and the number of rows tells us the dimension of the output space, or the codomain. So here, this matrix A can be associated with a linear transformation from R2 to R3 that's defined by taking any vector in R2 and multiplying it by A. And similarly, B can be associated with a different linear transformation from R2 to R3. And that means that when we add these two, we get a linear transformation from R2 to R3. But let's look at what this means in an example. So I'm claiming that t plus s is well defined. That is, it gives us a nice rule for taking a vector in R2 and producing another vector in R3. And so let's see how that works. So if I've actually done this right, that means that I should be able to tell you what is t plus s of the vector minus 3, 7. Well, by definition of addition of two functions or two linear transformations, this means apply t to this vector and apply s to this vector, and then add the resulting vectors together. Well, what do we get when we apply t to a vector? We get a times that vector. So that's minus 2. Sorry, I'm making sure I know what a is. 2, 0, 5, minus 2, 3, minus 6. So this is what this is, and positive 3 and minus 6. I gave myself not quite enough space to see what my matrices were. Now we have 0, 2, 4, minus 3, 2, 8. So that's what this is, right? I've applied the definitions of T and S, their multiplication by these matrices. And then what ends up happening, and I'm not going to go through the details of every step of the calculation, but our first entry in this vector is obtained by taking negative 3 times 2 and adding 7 times negative 2. And so we get negative 6 plus negative 14 is negative 20. And similarly, as I move down, I get 21. And then I get negative 15 plus negative 42 is negative 57. When I do the same thing to this matrix, I get this. And when I add these two together, I get this. Okay, so I skipped a bit through the step of doing this matrix times vector multiplication. And so if that was unclear to you, I recommend going back to the video that talks about that, how we multiply a matrix times a vector. But to take a step back, what I've showed you is that I have defined how to take a vector and use this transformation t plus s to take a vector in R2 and give us a vector in R3. So I have a well-defined function from R2 to R3. Hopefully this clarified if you were unsure what all this nonsense meant over here. That's what all of this is saying. It's just a description for how we take an input and get an output. And here I actually worked through it in this specific example. Okay. So what does this have to do with the addition of matrices that I talked about? Well, if you actually follow through, you can check that and I'll leave this up to you if you want to confirm this is true. It's a good exercise. That if we apply t plus s to our first standard basis vector, 1, 0, and work through this definition in the exact same way, what we'll get is 2, 2, 9. And if we apply t plus s to our second standard basis vector for R2, what we'll get is minus 5, 5, 2. And if you recall, what this means is that understanding linear transformations as vector multiplication times a matrix, the matrix corresponding to T plus S has 229 as its first column and minus 5, 5, 2 as its second column. And if we scroll back all the way to our example, that was what we got when we added these matrices. In other words, matrix addition is defined this way because it lines up with addition of linear transformations. We don't just do this because we can do it. We do this because we're thinking of adding two matrices as really representing adding the corresponding linear transformations. And when we add those corresponding linear transformations, this is the linear transformation that we get, the linear transformation corresponding to this matrix. I'm not going to go through it, but we could do the exact same thing for multiplication. So we could look at our linear transformation T defined here. And we could follow through what happens when we multiply this by a scalar. We could figure out what the matrix representation of that was, and it would be exactly the same as if we had multiplied the matrix A by that scalar. So this is why we define matrix addition and scalar multiplication this way. It's because it corresponds to adding and scalar multiplying linear transformations. So we're talking a bunch about addition and scalar multiplication, which is why we're all of a sudden saying, hey, wait a second, we're thinking of linear transformations as vectors, right? Vectors are things that we can add and multiply. And this, I think, can be super confusing because all of a sudden we're thinking of matrices as vectors, we're thinking of linear transformations as vectors. I thought matrices and linear transformations were things that acted on vectors, that sent vectors to other vectors. Remember, the definition of a vector is very general. So this is getting a little bit abstract. And so I'm going to summarize this abstraction in the following way. If T and W are vector spaces, and we look at all of the linear transformations between these two spaces, then we get another vector space. So stated in terms of our example, the set of all linear transformations from R2 to R3 is a vector space. Or if we think about this in terms of matrices, the set of 3 by 2 matrices is a vector space with this definition of addition and scalar multiplication. I want to flip over to our scary vector space axioms page, right? So this is, I forget the exact page. Let me look. Page 84 in Heffern's textbook. What I'm saying is that when you have linear transformations mapped from V to W, they satisfy all of these properties with the addition and scalar multiplication that we've defined. It can be, again, as I've said before, super overwhelming to stare at this and try to understand what's going on. But I think it's definitely worth kind of realizing that's what I'm saying, is that this addition and the scalar multiplication behaves in exactly the way that we would hope it behaves. So I'm not going to go and prove this, right? I'm not going to go through and go through each of these 10 axioms and say, hey, this is exactly why this is true. But I have a final, I guess, challenge to anyone who wants to. And so, I mean, you don't have to do this, but if you're if you're interested in the theoretical side of math, that is, you're either, maybe if you're a math major, I'd recommend thinking about this, or even if you're not, and these notions of proof are interesting to you, there are a few things in this video that I did not justify at all. And the first one I skimmed over, and so you may have missed this, but I call these challenge problems. So the first one is this. I just claimed, so when we defined addition of two linear transformations, and working through examples, you can pretty quickly see that addition works in the sense that it's well defined. I've told you exactly what to do with an input. If I've told you exactly, given an input, how to calculate an output, and there's no ambiguity, I've defined a function, but why is this function linear? Remember, a linear function is a function that respects the addition and multiplication of the underlying vector space, and I think that's not at all clear. So this would be one thing to consider for yourself. Try to either write a formal proof, or if not quite that, try to convince yourself, why is it that when we add two linear transformations, the resulting thing is linear and not just some function that's not necessarily linear? The second thing I would consider, if you want, is to go through these axioms and actually show that given two vector spaces, you could choose them if you want to make it a little less abstract. You could say, all right, let's choose functions, linear transformations from R2 to R3. Why is this a vector space? That is, go through each of these axioms and show that they're all true. I don't even necessarily recommend doing that though, because even like, I'm very much a theoretical math person. I love proving stuff, but showing that 10 axioms are true is really repetitive. And so when I'm looking at something, if I see a new vector space and I'm trying to say, okay, if someone's told me this is a vector space, I mean, I believe them, right? Because it's a trusted source, but I want to get an intuition for it myself. Usually what I do is I say, look, I'm not going to actually look at all these things. This would take way too long. The things I want to look at are, first of all, number 4. This is one of the easiest and often most interesting ones to look at. Sometimes it's not interesting at all, but what is the 0 vector? So think to yourself, wait, what linear transformation plays the role of 0? Sometimes it's obvious, sometimes it's not obvious. I would say this one is not totally obvious. I think that's often interesting to check. And then often the distributive properties are interesting to check. So 7 and 8 are two different distributive properties, right? It says that you have addition of scalars distributes over the multiplication, and you also have that addition of vectors distributes over the multiplication. And so you can either check that these are true, or even try to write out a proof that these are true. So anyway, these are just some kind of bonus ideas that if you're interested in the theoretical side of this, you might want to do. But you don't need to do this in order to understand what's going on. You can also just say, nope, I'm going to accept that I believe you, that when we add two linear transformations, we get a new one, and also that the linear transformations between two spaces satisfy all these properties.